to solve water-related problems throughout the world. The Water Alliance is especially in the last part of the circle to support the business side of the water tech related Dutch companies. And we do this together, for example, with the Cleveland Water Alliance, but also with other Dutch organizations like the Netherlands Water Partnership. Here in short, the water campus here at Leeuwarden, fundamental research, science at Wetsus, applied research at the CEW, that's also a strong education part in it. And all this targeted in the end, of course, to bring new technologies to the market, to the international markets. We have about 110 Dutch members. They are all water tech companies. And of course, predominantly, these are startups and SMEs. Not solely, but the majority is. We organize webinars as today. And furthermore, of course, are involved in business development, the whole broad range, matchmaking, and of course, branding and promotion. Here are some of our members. Some companies bigger, already well established, also in the US markets. Some companies entering. We see, of course, the whole broad scale of water tech related, drinking water, wastewater, and as we talked today, also surface water. I briefly wanted to touch base on some of the companies that are involved in the topic that we talk about today. Later on, we will hear about from Wetsus, Leon Korving, about his view also on the Dutch sector and P-load, phosphate load reduction. Another big player in the Netherlands and also in the States nowadays is the Algae Sonic, which I will give the mic to as well in a short while. Other companies involved, as an example, Deltaris, monitoring and modeling, also in the algae area. Or we, for example, have research institutes like NEO, KNAV, who is also very much involved in platforms for research institutions and local governments in making policies with regard to algae blossoms, battling, etc. KWR, together with Royal Haskoning GHV, did a lot of research and related to P and phosphate and monitoring. Just to name a few examples, it would be interesting for us, together to the Cleveland Water Alliance, to, at the end of this webinar, to get your input and to discuss if we can find input for possible next webinars. Hereby, I would like to give the floor to Algae Sonic as a renewed success story in the US market for some of the projects they're already realizing. So I would like to give the mic to Lisa Brent, please.
Yes, thank you, Harro, for the introduction. So we're indeed a Dutch-based company that provides environmentally friendly solutions for harmful algae blooms in lakes. We're developing innovative solutions, and at the core of this lies the fact that it has to be chemical-free and also can be used to reduce chemicals in the water treatment industry. Most of the solutions, and specifically the solution I will talk about now, is based on ultrasound to control harmful algae blooms, specifically for lakes and large water bodies. Well, we are already active globally. We have applications in drinking water, recreational water, and also in other applications that I will talk about a little bit later. So the MPC buoy technology, maybe can you click once more, Harro? Thank you. What is based on? Well, first of all, we've done a lot of research to how we can control algae with ultrasound. And based on this research, we found that if we use specific ultrasonic programs based on the type of algae that's present in the water, that we can selectively control the algae and also prevent resistant algae. So what our technology is basically doing, it's monitoring the water quality real time. And this is sent to an online server where we are predicting the algae. the algae blooms in the lake, and also defining in what stage of the algae growth they are at that point. And based on that information, the system automatically changes their ultrasonic parameters, so the frequencies, the waveforms, the pauses between the frequencies, to match the algae that are present in that water body. Next slide, please. So because of this, we also have our monitoring systems applied basically all over the world. At the moment, we are active in countries from the US to Latin America, New Zealand, and all these water quality stations are also sending us data. So we are receiving about 5.2 million data sets per year from all these buoys all over the world. And all these data sets we are combining with remote sensing technologies, so where we are using satellite images to get an overview of the algae accumulation and the algae growth over a lake. And with this information, we can also make a prediction model of the algae and work together with our customers to get a better view of what's happening in their lake, water quality-wise, and why these algae blooms start occurring. So next slide, please. And well, that has led to the fact that we are now actually providing a complete solution that starts from monitoring to predicting to also providing a control strategy. This is one of our latest projects. This was in a large cooling lake of a nuclear power plant, and they were actually also dealing with harmful algae blooms, and with a problem that this is at the moment they cannot discharge the water because the water quality is not good enough to be discharged on the surface water. So what is happening is that they cannot do any blowdowns of their cooling system, which is of course very dangerous for the cooling system and can cause a lot of damage. So this is a new application where we are also working quite actively at the moment, where we can really help to improve the quality of the cooling system, but also of the fresh water and also of the discharge water in the lake. So that was for now my explanation. We are working already again in different applications, and we can work for relatively large size lakes as well. So we have lakes up to 10 square kilometer in length that we can treat with our technology.
Okay, thank you very much, Lisa. Floor back to you, Max.
Oh, fantastic. Thank you both, Lisa and Harro, for sharing. Next up, we're going to have a presentation from our first, well, I guess now second, since Lisa presented as well, relevant expert within the space. This is going to be a presentation from Ed Verhamme from LimnoTech. So Ed, are you able to pull up your slides now?
Yeah, working on it here right now. Can you see? Does that work?
Yep, it's up.
All right. Oops.
Awesome. I'll mute myself here and hand things over to Ed.
Is it full screen? Can you see it full screen?
Nope, right now it's not in presentation mode yet.
Okay, it's going over to my other monitor here. Let me try.
Yeah, I'm doing too as well. It can be a little complicated. Ooh. Now we have just like a vertical bar. Now we have just the word harmful algae blooms really big. I like that. It's like highlighting the problem, you know? This is really what we're here to talk about. Right.
Let me try and reshare here.
When you're sharing, you should be able to select which monitor you're sharing from.
All right, let me try that.
All right, we see it not in presentation mode yet.
Oh man, okay, when I go in presentation mode, it goes to my other monitor.
Okay, well you can click through here if you want, or you could just share your other monitor, whichever you prefer.
Let me just try to share the other monitor, hold on.
Yep.
All right, is that full screen now?
Yep, that is beautiful.
Okay, All right, thanks, Max, and thanks for the opportunity to talk about harmful algal blooms. I think the topic of this webinar is best practices in harmful algal bloom. I think I was going to preface my presentation with just calling it sort of my practices or my overview of what we've been involved with. LimnoTech's an environmental engineering consulting firm. We've been involved with many aspects of harmful algal bloom. So, I'll try and touch on a couple different aspects of what's involved with the bloom. There's research, a lot of very fascinating, in-depth research happening right now on Lake Erie and actually across the Great Lakes. There's a lot of stakeholders, industries, drinking water treatment plants, fishermen, members of the public that are generally affected. So I'll try and give a little bit of a broad perspective. And I just wanted to start with this. I actually just came across this today, and to me, it really shows how the algal bloom issue has gone down to the awareness of the general public. This sort of illustration sort of is an artistic representation of the algae that almost ate Toledo. This was in 2015. This story was published, and it really did affect daily life in Toledo and throughout Ohio and really throughout the country. I think it's easy to forget sort of where we were in 2014, where we are today. So I think it's nice to sort of look a little bit back at the past. And this slide here just shows a lot of different visual representations of what we're talking about for Lake Erie, what's at stake. The algal bloom up in the upper left, massive, covering hundreds, thousands of square kilometers on Lake Erie. Scientists are trying to predict the size of the bloom every year. It's impacting shorelines and really just the people's perceptions of the health of the lake. What we're sort of talking about is this annual recurrence of the harmful algal bloom. So this is a satellite representation of the peak of the bloom every year. And we can sort of see from 2002 to this one ends at 2016, but we have more recent ones, just showing how there's such a variation in the size of the bloom where it impacts the most. But generally it's July through September impact. One thing that I do want to highlight is how industry has really stepped forward and partnered with scientists quite a bit. How do we get monitoring equipment out on the lake, and how do we sustain continued observations of this problem? I think we can see that the satellites can see the bloom when it's cloud-free. How do we monitor the bloom on the ground? So we've been working really across the Great Lakes on getting continuous observations, partnering with the Great Lakes Observing Systems and NOAA to really manage a lot of these new data feeds. One buoy project in particular, or monitoring project that we've worked on, is working with the city of Toledo. So in the days after the Toledo water crisis, we were able to get a monitoring station up and running at the Toledo water intake crib. You can see it here in the background. And really what this is it's the ears and eyes on the water. What's happening out on the lake where the city of Toledo and other water treatment plants are drying their source water? How can we monitor this very large water body and understand changes that are happening? I think Lake Erie is the shallowest of the Great Lakes, and especially this part. So it's prone to fast changes from weather and wind and water inflow. Oops, sorry. Again, just a little visual orientation. The city of Toledo on the Maumee River. The Maumee River is the largest tributary on Lake Erie, other than the Detroit River, which is more just draining the upper Great Lakes. So the Maumee River puts out a lot of nutrients, a lot of suspended sediment, and we can get a little orientation on where the city of Toledo water intakes are. With these sensors that we've been able to install, we're using YSI, EXO, series sondes, and monitoring, really using their total algae sensor, which is measuring chlorophyll and phycocyanin. So this graph here shows the phycocyanin daily average results in the green lines, and the brown dots are the city of Toledo's raw water microcystin data. So really, before any treatment is applied, what's happening in the lake? How can we understand the sort of toxic algal trends in the lake, and get some indication of how real-time data can help understand what the lake is doing. So I think we see a good correlation between sensors and the assay microcystin results. So these tools help water treatment plants. They help beach managers understand conditions. We can move towards beach forecasting models and understanding what's the risk to swimmers as well as folks upstream and downstream. One unique aspect of the 2017 bloom 2 years ago was that it went a lot further up the Maumee River than we've seen before. So there was a particular risk to people rowing in the river. You can see in the right, there's a crew boat on the right. So, understanding risk and exposure and having real-time sensors to understand trends and how the water bodies are changing. This is a look at all of the sensors that are currently monitoring harmful algae in Lake Erie. This is part of the Great Lakes Observing System's HABs monitoring network. So, we've sort of partnered with researchers and with these water treatment plants to install real-time sensors. So it's one of the, I guess, one of a kind in the Great Lakes in terms of the diversity of organizations working together, sharing data, and really trying to interpret in real time and through research projects what's happening with the bloom and how can we better forecast conditions. Another project that we did this year is, so I talked a little bit about the satellite observations and how we have these continuous sensors at particular locations, but what we're lacking is some broad scale grab samples of water. There's a lot of things that we can't have a sensor measure. So grabbing a sample of water, taking it back to the laboratory and sort of running a barrage of tests to get some idea of some spatial differences in genetics, in nutrients. So in 2018, we did a 100 grab sample event with the University of Toledo, Bowling Green State University, and Ohio State University under funding from the NOAA EcoHab program. So this is the microcystin results from that day, so we can get an idea of how varied toxin levels can be, algal toxin levels can be across a very broad area. This is about 40 miles across from east to west. And so, again, just another suite of sampling that helps us understand how conditions are changing. And this understanding allows us to develop interpolation algorithms to understand the sort of spatial variability that we might see in a satellite image versus actual toxin concentration. So we're going to be continuing this in 2019 as well. One component of the algal monitoring on Lake Erie is collaboration. I think we all know that there's a lot of folks studying and working on particular aspects of the bloom. So, we routinely get together. This particular event we're talking about here is how we clean and calibrate all of these sensors at once. So how do we ensure that they're having a consistent reading between values and producing good data throughout the season. This particular event and project, we're actually hosting another cleaning and calibration event next week in partnership with the Great Lakes Observing System. And so we're, again, just how do we keep collaborating and working together? Another tool that we consistently use is the seasonal forecast. So we can predict with pretty good certainty what the size of the bloom is going to be for the coming year. So this event happens in early July. Typically, by late June, we have a good understanding of the amount of phosphorus that's come down the Maumee River, and we can use that information to predict the size of the coming bloom later in the summer. So this is put in partnership with a lot of different organizations, contribute modeling expertise, as well as sort of the satellite pairing of the correlation of the size of the bloom to the amount of phosphorus that's come in. Again, just zooming a little bit closer on these two key graphics. In particular, the lower right, we can sort of see the cumulative phosphorus load coming down the Maumee River. There's a fantastic program run by Heidelberg University to monitor nutrients every day and understand the amount of phosphorus, nitrogen that's coming down the Maumee River. So this data set can help us really know what's happening this year, but it can also help us monitor progress. So as we implement nutrient reduction strategies and best management practices, are we seeing a reduction in phosphorus? There's the harmful algal bloom bulletin that comes out throughout the algae season. This is an example of one from 2017. It just kind of gives a synopsis of the current condition of the bloom, a general statement and discussion of some conditions that are happening out on the lake, as well as later in the bulletins, a little bit of a forecast of where the bloom might be moving in the future. I did want to point out that we're really doing an unprecedented amount of monitoring on Lake Erie. This map here shows all of the all of the monitoring instruments that are in Lake Erie. This was last year, so every dot represents an instrument deployed for either the whole season or part of the season to monitor continuous observations from a part on Lake Erie. And most of the dots that you see, the red sort of diamonds, are from the Great Lakes Acoustic Telemetry and Observation System, which is a fish or animal tracking network. So really tracking walleye and fish movement across Lake Erie. And the other dots are surface buoys or sensors at water treatment plants. So, if we were to look at this map from same map from 6 years ago, 7 years ago, there'd only be about 4 or 5 dots on this map. So just a big increase in the number of sensors or things we're trying to measure on Lake Erie. And I only see that increasing. So, we're already planning for 2019 to put more sensors out. So as we sort of increase the number of sensors, it's becoming more important to manage data and really information well from these systems. I did want to also mention real quick that one initiative that I've been working on is how we, with this increase in sensors, how can we have a wireless sensor network that can help support sort of the data telemetry side of getting these observations back to shore. So we're working on a rollout of a wireless sensor network in Lake Erie to help get data back to the internet and back to our application or our decision makers easier. We held the meeting here in Ann Arbor on Monday. So we had about 50 people talking about technology and really how we bring sort of new cutting edge wireless technology to the Great Lakes community. Models are also a significant component to understanding harmful algal blooms. I think we can only be out on boats so many times to understand what's happening. So we've been working with models and how to really use our mathematical understanding of how water moves, how nutrients are moving throughout the system, and how that turns into harmful algae, and then how we subsequently manage restoration efforts going into the future. Again, models are really good at matching existing bloom conditions. This is showing the model that LimnoTech maintains to predict the peak and sort of really run up to how big is the bloom going to be in a particular year. So we can match data from the University of Toledo well in the years that we simulated. With just a few remaining minutes that I had, I just wanted to point out some resources that I use and that are good follow-up points to learn more about what information and research is being done. This is the website of the Great Lakes Environmental Research Laboratory, their HABs on hypoxia page. A lot more information, a lot more in depth. I also wanted to mention the Great Lakes Observing System. They have a great back-end network and data management system, and we also partner on various products on user community. So how do we get data to the people that need it? Ohio Sea Grant has been marshaling a lot of the research projects in Lake Erie. So if you want a list of dozens upon dozens of research projects and what's happening right now, you can check out their website. And I think with that, I'll just end with just buoys. I think, we're always trying to get smaller and more efficient buoys to measure what's happening on the Great Lakes. And please feel free to follow me on Twitter. I try and post a lot of updates about what's happening and really engage in conversation. So I think that's a great venue for engaging with folks past this webinar.
Fantastic. Thank you so much, Ed. That was extremely informative. Before I hand things over to Leon, which I'll do in just 1 second, I'm going to go ahead and launch a poll for the group. I'm going to try and reposition it out of hopefully it's not dominating the screen. This is a follow-up that we'd like to see from, any folks that are interested that are attending right now about what kinds of future webinars, future collaborations between the Water Alliance and Cleveland Water Alliance, between the Netherlands and the US, you'd like to see us follow up. So if you can complete that as Leon is talking, and also as we move into question and answer after that, that would be extremely helpful. But with that, I would love to hand it over to Leon. Leon, you should be unmuted now. And if you're able to share your screen, if you move down to that bottom bar, you should be able to get your slides up. Awesome. And is the poll like in the way of your slides in any way? Is that showing up?
Not on my screen, but.
Okay, great. Fantastic. All right, well, feel free to jump in then, Leon. Thank you so much.
Okay, thank you for the kind introduction. In my presentation, I'll try to give a bit of the European perspective on control of surface water eutrophication. I've taken the topic a bit broader than just harmful algae blooms, and also want to look at eutrophication as a problem as a whole. And algae blooms are, of course, the big symptoms of the larger problem of eutrophication. I work for Wetsus, and Wetsus is a water technology institute, so we do fundamental research on developing new water technologies. We don't focus so much on water quality issues. We have other institutes in the Netherlands like Deltares and KWR that also focus on that. I have included some slides with the work they do as well to give a broader overview of what's happening in the Netherlands. So if we look at the situation in the European Union, an important regulation for the European Union is the Water Framework Directive that came into force in 2000. It requires all the European member states to make water basin management plans and to ensure that the water quality in the surface waters has a good ecological status. And this Water Framework Directive has initiated the realization of more than 130,000 monitoring points all over the European Union. And the countries have to report about the water quality to the European Union. If we look at the current situation, the last report came out in 2018. It showed that only 40% of these monitoring points showed a good ecological status. So that implies that 60% still have something to do about their water quality. The good ecological status is based on both biological elements and physical chemical elements. So it's a broad survey that you have to look at. If we look at more specific to the Netherlands, of course, we also measure have monitoring points for this Water Framework Directive. The map to the right shows the results of agriculture-dominated headwaters in the period of 2000 to 2010. This is a publication that's been made by Deltaris in the Netherlands. And they showed that if you look at nitrogen and phosphate, the main nutrients controlling eutrophication, that's only about 50% of the monitoring points are compliant with a good ecological status. They also looked at reduction of nitrogen and phosphorus trends over the last years, and you see a slight decrease, but as you can see in the figures, the decrease is very slow. So we still have a lot of work to do to really come to a good ecological water also in the Netherlands. If you want to control eutrophication, I think it's good to realize there are two pillars. First of all, it's good that we know what problem to address, where do we have issues with eutrophication, in order to be able to define mitigation actions to control that. First, in my presentation, I'll be going a little bit into some work that's being done in the Netherlands on monitoring and modeling. And then later on, I'll come to the mitigation actions we can do. So if we look at monitoring, of course, a lot of work is already being done in the framework of the Water Framework Directive of the European Union, but these are sampling stations where samples are being taken once in a while. We're also working in the Netherlands on more direct interaction with the stakeholders, for instance, via a nitrate app that's been developed by Deltaris, where farmers can very quickly determine the nitrate levels in the water and get feedback on the actions that they have taken themselves to ensure that the water quality in their fields is becoming better. It can also be used by authorities to control illegal spills and to determine main transport routes of pollution. In addition, Deltaris is also working on combining different models like hydrology models, water quality models, and management tools, and combine that to get an algae radar system where you can predict algae blooms in advance and try to act beforehand. I believe Deltaris is also in the call, so later on, if there are specific questions about these tools, they can be directed directly to Deltaris as well. We have heard also about Algae Sonic and their buoy system, which is actually a combination of monitoring and control. So they get a lot of data with their buoys about the water quality, and then use that data to take action and control the algae blooms, as Lies has explained before. But when you want to control eutrophication, I think it's important that we also go to load reduction, and that has not been discussed so much in this webinar so far, and I'd like to go into that a little bit deeper in my presentation. So to the left, you see a graph that shows that there are actually two states of a freshwater system, where the red line shows that a freshwater system can accept a certain level of nutrient loading and stay stable in a clear water. until a certain threshold is being reached, and then transcends into a turbid system. Once you start reducing the nutrient loading, there are stabilizing mechanisms that will prevent the system from becoming clear again. So you will really need to go very low in your nutrient loading to come back to the original state again. So to the right, you can see 4 approaches. So you can have a temporary approach where you try to mitigate the algae blooms and try to control the blooms by having mitigation actions like ultrasonic treatment or adding chemicals to the system. But if you do not reduce the loading, you will always have to risk that the next year you will have these algae blooms again, and you have to again mitigate these algae blooms. You can approach B is an approach where you reduce nutrient loads, and it's to a certain level. And it's often also what we see in the Netherlands. It's very difficult to go back to the really low nutrient loadings that are needed to come to a very clear system by itself. So if you would be able to reduce the nutrient loading to the level of B in the graph, it will not, the lake will not restore to a clear system by itself. But for that, you would have to do an ecosystem reset. So that, for instance, by having a treatment, a geochemical treatment, for instance, by adding phosphorus or removing lake sediments or removing fish from the lake to be able to come back to the clear system. And once you're back to the clear system and the nutrient loading stays stable, you are able to get to a clean system back again. Approach C is, of course, the most sustainable approach where you could reduce the nutrient loading to very low levels again, and that the system will always stay clear. If you look at load reduction, we have to understand what are the important sources of mainly phosphorus, as both phosphorus and nitrogen are important sources of important reasons for algae blooms. But we in the Netherlands, I think also in the United States, we realized that phosphorus is the main way to control these algae blooms. That's why I'll focus on phosphorus in the coming slides. When we look at phosphorus, we see that in most cases, sewage effluent and agricultural release are the main sources of phosphorus loads to our surface waters. And I'll go into both loads in the coming presentations, coming slides. So if you first look into sewage, in the last decades in Europe, we've been able to reduce nitrogen and phosphorus loads from sewage by having enhanced phosphorus removal in sewage treatment plants. This has been initiated by the Urban Wastewater Directive of the European Union. And to the left, you see a graph of the River Rhine, where you can see that from 1985 onwards, due to enhanced phosphorus removal in sewage treatment plants in Germany, for instance, the phosphorus loads in the Rhine have really decreased dramatically. To the right, you see a graph of nitrogen and phosphorus removal in the Dutch wastewater treatment plants, and you see again that around 1990 we started implementing enhanced nutrient removal systems in our sewage treatment plants that came into full effect by 2010, and that stimulated reduction of phosphorus levels in our rivers, as can be seen in the graph to the left, for instance, in the Rhine. But it holds true also for other rivers in the European Union. I already mentioned the Urban Wastewater Directive. This is the European directive that's introduced in 1991 that requires all European member states to implement nutrient removal technologies in their sewage treatment plants. And the most stringent treatment is required for sewage treatment plants that discharge to sensitive areas. And in fact, that are most sewage treatment plants. And these sewage treatment plants need to remove phosphorus down to 1 milligram per liter, or have an 80% reduction. And for nitrogen, they have to remove down to 10 milligram per liter, or 70 to 80% reduction. And in the graph, you will see that the blue line is the compliance rate of European member states to this more stringent treatment criteria. And you see that currently more than 90% of all sewage treatment plants in the 15 member states, original member states of the European Union, comply to the Urban Wastewater Directive and the most stringent treatment limits. We also have a relatively new European member states, mainly Eastern Europe member states in the European Union, and the light blue line shows that they are also realizing enhanced nutrient removal systems in their sewage treatment plants. I've tried to also compare this to what's happening in the United States, and I found a publication by the Water Environment Federation, and that shows that there are quite a lot of differences, as I understand, in different member states of the United States in phosphorus removal. Some states have all sewage treatment plants have phosphorus removal systems in place, but there are also a lot of states that still have no phosphorus removal. And it would be interesting maybe for the discussion to understand where is this difference between the European Union and the United States on phosphorus control from sewage. If you go to agriculture, of course, agriculture is an important input to nutrient loads to the surface water as well. And this graph shows the improvements that have been made in the last years in getting a more balanced nutrient input to the fields. So there are requirements in the different member states to not put more nutrients on the fields than is actually taken off by the crops. The red circle shows the improvement that's been realized in the Netherlands from 2003 to 2013, and it really shows a big reduction in phosphorus input to the fields. Nevertheless, we still have huge historic phosphorus loads in our soils, as can be seen in the graph to the right, where you can see that in the Netherlands there are some really black spots where we have still high phosphorus levels in our soils due to historic fertilization, over-fertilization with phosphorus on our fields. So there's still a lot to do there. So despite all these efforts to reduce loads from sewage and agriculture, we still see that we are not there yet, as I showed already in the first slides. And we still have to go further in load reduction to be able to obtain good ecological quality. And for that, at Wetsus, we are looking at methods to go to even lower phosphorus removal technologies. And we see that adsorption is probably one of the most interesting technologies that can be applied to go to really low phosphorus levels to treat, for instance, effluent of sewage treatment plants and agricultural runoff waters. The advantage of adsorption to, for instance, halophyte systems is that it has a much lower footprint. Can be 100 times smaller than current halophyte systems. This is a picture in the slide of a stormwater treatment area in the Everglades, where we're currently participating in the George Barley Water Prize contest, and the blue service area shows the service area you would require only for adsorption. So that has a huge benefit on service footprint. Already in the Netherlands, we are doing some tests on using iron-coated sand to adsorb phosphate from agricultural drainers. These are some slides. This is a slide from projects that are being done by Deltares in the tulip bulb growing region in the Netherlands, where tests are being done with adsorption systems on the side of the ditches to remove the phosphorus from the agricultural ditches, or even have drainage pipes in the land that are coated by iron oxide sand to capture the phosphorus before it flows out to the surface water. These systems just adsorb the phosphate and have a long standing time of several years. But if you have to start removing higher loads of phosphorus, it will be important to be also able to regenerate the adsorbent. And that is a project that we are working on at Wetsus together with our industry participant Aquacare. And here we've developed a system to remove the phosphorus on high capacity adsorbents, and we can then regenerate the adsorbent to take out the phosphate again and recover it as a concentrated solution that can be used as a fertilizer. This concept has already won prizes in the bonus return competition around the Baltic Sea, where they also suffer a lot from algae blooms. And the concept is is now a finalist in the George Bardi Prize after pilot test runs in Canada last year. And we will install, together with 3 other competitors, we'll install a 2 MGD installation in Florida in 2020 based on this system. The system can remove phosphorus down to 10 ppb of levels and is cost effective. So I'll now end my presentation. I think the Netherlands is, as you may see on the slide, is on the end of a big river system. So we are the sort of the drainage pit of Europe, with the River Rhine flowing all the way from Switzerland and Austria through Germany to the Netherlands. And we get all these nutrients in the Netherlands. We have a very dense population of 16.3 million people, a lot of agriculture. So nutrient control is something that we have to do. We are not there yet, and we are interested to learn and exchange experiences with the people in the United States to see how we can control this wicked problem. Thank you for listening. I'll give it now.
Thanks very much, Leon. That was extremely informative. And thanks all who attended the webinar. Unfortunately, as you all can see, we've made it to the top of the hour. So we don't have time for the panelists to respond to questions at this point. I will circle back with the folks who attended the call. We've had a couple of questions submitted to see if we can get those answered. But unfortunately, we don't have time to do that on the line right now. But thank you to all who attended, and thank you very much to Harro, to Leon, to Lisa, and to Ed for presenting today. This has been extremely informative. We will be processing kind of a short recap of this video, as well as we've recorded the entire thing. So we'll be passing that along to attendees for if you want to reference back any of the content that was covered. As always, please feel free to reach out to us directly if we can answer any questions. And thank you all very much for your time. All right. With that, I'm going to end the meeting, and we'll all talk soon. Bye now.